for the second talk of this morning by Tomas Prochazka from Czech Academy of Sciences about the W-algebras and ODE IM correspondence. Please, thank you very much.
So it's always a pleasure to be here. So what I want to talk about today is how kind of this algebraic things, so W-algebras, which are some extensions of Virasoro algebra, see some nice geometric structures that one knows, for example, from four-dimensional supersymmetric field theories or from topological strings and so on. So what I want to do is very shortly remind you what are W-algebras, but since I already explained it in much more detail a few years ago, I really make this part much shorter. So hopefully, you can get, I just summarize the things that I think are needed for the rest, but don't go into too much details. Then I focus on this integrable structure. So the algebras have some kind of infinite collections of commuting quantities, and the question is how these are diagonalized. So these are these two steps here. So I want to explain how Bajanov, Lukyanov, and Zamochikov kind of describe the spectrum, so the eigenvalues of these commuting quantities. And then, in order to extract explicit formulas, this is something that I did with my colleague. We used the WKB calculation, and there is very nice geometry that shows up when one does this. And finally, if there is time, if one wants to understand these things, kind of to resum, like generating series containing all these eigenvalues, one encounters that the series are not summable, so there is very nice resurgent structure of these generating functions of conserved charges and so on. So if there is time, I will mention that. But this is something that we are working on currently, so this is more like the idea that there are very nice things, there, but I still need to understand those better. Okay, so here there are a few slides summarizing what W-algebras are. So I consider family of algebras called Wn, which are extensions of Virasoro algebra by some higher spin fields. So roughly, if you see any construction of Virasoro algebra involving SL2, if you replace SL2 by SLN, then you get Wn. If you like some kind of brain constructions and so on, whenever you have SU2 gauge theory for two brains, instead of two brains, if you have n brains, then you have Wn. So it's a very natural thing and basically unique thing that has this property. Okay? And for many things, it's useful not to consider individual Wn algebras like W3, 4, 5, and so on, but to consider kind of large n limit, which is which goes under name W infinity, sometimes W1 plus infinity. And the main point is that there is a careful way how you can take this limit of n going to infinity in such a way that you don't lose this parameter n. Okay, so this is like one of the important things that we learned maybe more than 10 years ago from work of Gabriel and Gopakumar. So originally I had kind of, for each integer n, I had one Wn algebra for any central charge. So we had two parameters, but now this W infinity has kind of two continuous parameters, and they are conveniently parameterized by three numbers modulo this constraint. Okay? So for example, the central charge is function of this and so on. Okay? And once you understand, so this is like big algebra with just infinitely many generating fields, one for every spin, but it carries exactly the same information that this whole family. Okay? So this is just like convenient way how to encode the information. So for example, if you look at OPEs of this algebra, and you choose one of these parameters to be n, then you recover exactly OPEs there. So, okay? And one more thing that I should say, that this is kind of more general thing of the version of what I just said. Now, if I specialize these parameters, so if I impose additional constraints on them, like constraints of this type, then I recover all the, let's say, minimum models of Virasoro algebra, or more generally all the minimum models of Wn algebra and so on. So this is really one nice family that kind of contains a lot of things that you possibly encounter at some point.
So can
understand. So the way I should think about the three lambdas is that there's a multi-parameter way that you can take the large n limits, keeping the three lambdas fixed in this particular way. Is that?
You can take some large n limits, but if you send one of the lambdas to infinity, that's like sending n to infinity, for example, then this equation tells you that the other two differ by just sign, so there is one parametric family of this kind of large n limits in some sense.
Right. Okay.
But there are, honestly, if you look at it carefully, there are three large n limits.
There's roughly three large n
like
limits. Okay. Yeah.
Depending on which one you send to infinity. So if you know this ADS3 CFT2 holography, there is in one of those large n limits, you are two of those limits you are keeping n fixed and send C to infinity, while the other one you are kind of fixing the ratio, like some kind of prof limit.
Right.
So from the algebra point of view, they are kind of equivalent limits. They just differ by permutation of these. But on the level of representations, those that, for example, Gabriel and Gopakman studied, those are not symmetric under this, so the limits are different. Okay? But the algebra itself has those three limits are kind of equivalent.
And to what extent do you care about unitarity here? You want to
Usually when you impose these constraints randomly, then you end up with something that is not unitary.
Exactly. Yeah.
But if you choose this, for example, to be n plus 1 and 0, then those are all the unitary minimum models of all Wn's. So,
but you will treat them all on the same footing, independently of unitary.
For what I care about, it doesn't really matter. And in fact, I will, for the second half of talk, I will consider a case where you impose one constraint when you put lambda 1 to n and lambda 2 to k. So two constraints like this. Then I get non-unitary ones, but they correspond to VOS associated to unitary for the superconformity theories like via this raster beam and friends.
Yeah.
So the for the unitary lead to something that is not unitary from this point of view. And those are the ones that I care about more.
Okay, thanks.
Any other questions? So this is like, the message of this is that there is intrinsic family of algebras, a specialization in coordinates contains many things that we know, and it's conveniently parameterized like this by two complex numbers, let's say. And then,
sorry, what is the specific values corresponding to Ising or Liam?
Ising is, for example, when you put lambda 3 to 2, that's kind of Virasoro reduction, and then the other two you put 2, 1, 0 here, 2, 1, 0. So you put.
And so you're getting Virasoro.
You can get Virasoro also. If you choose
Ising, you're getting Virasoro. Yeah, no.
It's special case when n is 2. Yeah. So the rank 2 case is Virasoro, rank 3 is W.
Okay.
Yes. So it contains most of the things that I talk about apply exactly also for Virasoro as the simplest, let's say, specialization of this. But the whole point is that most of the things generalize from Virasoro very easily to any rank. So and it reveals more symmetries and so on. So it's useful to consider this more general setup. But sometimes I will, for simplicity, specialize to Virasoro just to make equations simpler. But everything is kind of very similar for Virasoro as well. And that's the special case of this when one of these lambdas is 2. Okay? Now, in this parameterization, you see that it's kind of symmetric under permutation of the three parameters. And that's not just the artifact of this parameterization, but it is underlying symmetry of the whole representation theory. So, for example, this picture illustrates it. So these curves are kind of lines or curves in parameter space, in this two-dimensional parameter space of the algebras, where the vacuum representation has some null state. Okay? And this is sign of having some minimum models or Virasoro and so on. So you can imagine that one of these curves corresponds to n equal to 2, so to Virasoro. Another curve can correspond to this 2, 1, 0 curve. And when those two things intersect, there will be Ising model sitting there and so on. Okay? But you see that it has this like rotation symmetry by 60 or 120 degrees. And that's kind of underlying symmetry, discrete symmetry that this algebra has. You see it even at other places of the representation theory. So for example, if you enumerate all the fields, all the local fields that you have in the algebra, it's quite easy to see that it is given by this counting function. So this is kind of like free boson if this n wasn't there, but putting this n here gives you the vacuum character of this W 1 plus infinity. And it's known since 19th century that this same generating series is also counting three-dimensional Young diagrams. Okay, so this is some kind of coincidence that is not an accident. So actually, counting-wise, you can identify all local fields in the algebra with some configurations of boxes that you stack in the corner of the room. And then this triality symmetry, the symmetry permuting lambdas, is exactly the symmetry which permutes the coordinate axis. Okay? So many symmetries of the algebra and properties are very simply reflected in this combinatorics.
Sorry, and this is the W infinity one that you wrote
Yeah,
down?
this is the vacuum character of W infinity if I keep the parameters generic. So I don't impose any of these
Okay.
specializations. Yes?
Okay, so it is a vacuum module.
That is the vacuum on this.
And why you have Q? Because like
Why I have what?
why you have, for example, the character it is there is one state at level 1.
Yeah, so that comes that I didn't want to spend much time about. So for counting,
is
it's better to
plus
consider
infinity.
W1 plus infinity. So this is W infinity where you add additional decoupled free boson. Okay.
Okay, so this
So
is
then
like
this
okay, so it is
Q1
W1 plus infinity.
This
one.
is just the current of this spin 1 free
Yeah.
boson. 3 is just that you have Virasoro generator, then you have derivative of this and square of this. So you have Sugawara of this, then its derivative, and the new independent T. Okay,
And you don't have the modes of all the other infinite currents.
I mean, in vacuum representation, they annihilate the high
Then
state
C
state, so
already
they
did
only
what?
show up as higher
Okay,
but
but-
they are all of them. Yes.
Okay.
You can think of this if I call the free boson like J and
Yeah.
Virasoro L.
And
This
this
is like J minus 1, this is J minus 2, J minus 1 square, and L minus 2, and so on. And L minus 1 kills the vacuum, so that's why it doesn't contribute here. You know, the counting is very simple, I can show you maybe
Okay,
later.
okay.
And in the sixth, there's, I don't know what to call it, W minus 3, the thing that corresponds to the spin 3 currents.
That will be here. Yes.
In the sixth, yeah.
Yeah, you would have
Yeah,
three
you have
things coming from the free boson, then you have the J, T, T prime, and then you have new one, and so on.
And then
So
the
at
new
every new spin there is one new generator, and then its Fourier modes kind of propagate all the way. And that's why there is this factor 1 minus P2 and 12. This is very easy to see from the W-algebra point of view that it's counting the vacuum character. What is not easy to see is that this function counts boxes. Okay?
Right.
That is the complicated part. That the combinatorics is counting this 3D and diagram.
And the situation at finite n is much more complicated, right?
Not much more. So this is what I have on the next slide.
Ah, okay.
So choosing lambda to be n instructs you to truncate in one of the directions to have only n, at most n layers.
Okay.
So that's very simple. Yeah, first of all I have picture for other primaries, not necessarily for the vacuum. So if you have some other primaries, yeah, this is the thing that I just told you, that if you choose Wn, then you have at most n boxes in one of the directions. But you can also choose different primary, like not the vacuum, but some other primaries, and then you choose which primary you have by allowing infinite piles of boxes in the 3 directions, which are labeled by like triple of Young diagrams. Okay? So this is how we control primaries. And again, you just count in how many ways you can add boxes in this finite central part, and that gives you the characters. Now I'm having special primary and the generic parameters. Okay? But you can also combine it, these two things. So changing parameters of the algebra, like restricting the parameters, specializing them, and choosing primary, and that gives you nice counting, which counts the characters of all the minimum models. Okay, so you end up with having some kind of periodic tilings of playing these configurations. So for example, this one is Liang model with delta minus 1/5. This one is the vacuum of Liang. You can count in how many ways you can periodically add boxes, and that gives you exactly the character. This is the Ising model, the vacuum representation, and it has level 6 null state, which you see here that there is this box missing and so on. So a lot of things that you know from like Francesco or so, you see that they have very simple combinatorial interpretation. Okay, so this is like kind of useful way.
Is there any simple way to see P and Q?
Yes, like P and Q are related to how is this thing shifted. So here, this thing, so this is 2, 3 kind of, you know, this box that is missing. And if you move it like in this direction, you are increasing P and Q, for example. There is some shift, like P and Q you have to shift by 2 or something, but it's really controlling. So here, in this vacuum representation of the minimum order, there is this height, 2, which is telling if it is Virasoro algebra or some higher. And then there are these two parameters, this P and Q, which tell you what is this offset between this and this. So for example, yeah. Yes, so this is like, there is this nice algebraic structure that you actually only reveal nicely if you go beyond Virasoro algebra, but it applies also to Virasoro. Now there is a completely different way of writing the algebra, but this is also something that I talked about 3 years ago, so I want to say it very quickly. So there is very different description of the full algebra, which is explicitly given in terms of generators and relations. So one can, it's like kind of sophisticated way of writing harmonic oscillator in some sense. So there is infinite collection of commuting quantities, and then there is infinite collection of ladder operators which add or remove boxes, and the relations between them, they are a little bit nonlinear but can be written explicitly on one page, but I want to save you from this. And you can derive these things explicitly using algebraic beta ansatz. So basically, there is an object called, by some people, instanton matrix that was found by Maulik and Okunkov. It's very closely related to Liouville reflection operator, if you are more familiar with Liouville theory. And it satisfies Yang-Baxter equation, and if you have something that satisfies Yang-Baxter equation, there is this whole machinery of algebraic beta ansatz which allows you to construct commuting quantities, ladder operators, and fine spectrum in principle, and so on. Okay? And in this picture, this algebra is really like Yangian of the free boson. So what is happening is that you start with free boson, and then you can, this is like spin chain of length 1, and then making the spin chain longer, adding like additional sides of the spin chain, increases the rank of the algebra. So this would be rank 1. Then for 2 sides you would have this plus Virasoro. For 3 sides you would have W3 and so on. So this kind of Yangian level corresponds to the rank of the algebra. Yeah, and as I said, Virasoro would be given by just spin chain of length 2. And finally, this is like one picture where I wanted to get. This kind of combinatorics of this elementary box that you are putting in this box counting picture, and its associated kind of rational function which has zeros and poles on these like vertices of the box. That is kind of the only structure constant that one needs to specify in this Yangian picture. So the whole complicated algebra with infinitely many fields of higher spins and so on can be written in terms of some exchange relations for these ladder operators. And they roughly, like as an example, they look like this. So if I exchange the generating function of these Hamiltonians with my box addition operator, so I exchange their order, then I just need to multiply it by this place factor. And this one is just really a rational function with just 3 poles and 3 zeros. Okay, so very simple degree 3 function. And these parameters epsilon that I write here, they control which specialization, what is the central charge, or what is the rank of the algebra, and they are roughly inverses of those lambdas that I had before. So the constraint that I had at the very beginning, that sum of these lambdas is 0, so that only 2 of them are independent. That one is written in terms of these epsilons as this, and some people call this like WL3 conditions. There are different ways how people think of this. Okay, but it's again constrained on the parameters. So the algebra is parameterized by 2 independent complex numbers. Okay. Good. So this was like a review, very short review without any equations. But like what is important is this kind of structure of the box, and then this unique structure constant. Now I already showed you that there is infinite collection of commuting quantities that the algebra has. They are kind of Hamiltonians that you can diagonalize. And actually those that I mentioned here that are kind of obvious from this Yangian point of view, those are very easy to diagonalize. And actually their spectrum in representation in representations is very simply described by combinatorics of these 3 partitions. Again, a few weeks ago you could have seen some formulas for it, but basically the eigenvalue corresponding to this thing is given by some product over all boxes in your configuration weighted by positions, geometric position of the box. Okay, so it's very concrete, and you can rewrite the spectrum completely. And then also the action of this E and S. But unfortunately, from the conformal field theory point of view, these Hamiltonians, these commuting quantities, are not so nice because they are not local, so they are not given by some zero Fourier modes, some local currents, which has some drawbacks. For example, if you want to study how these things transform under modular transformations and so on, it's really, if you lose the locality, it's really kind of annoying to, difficult to say anything about those. Okay? On the other hand, there exist more general choices of these commuting quantities. So what I'm talking about is, if you think of this as being kind of Cartan subalgebra, so collection of commuting quantities, there are different inequivalent choices of this subalgebra. So there are different choices of commuting quantities which have very different properties. Okay, and then this spin chain or algebraic Bertansatz picture allows you to construct like a family of these things which is parameterized by some additional parameter, which let me not go into it now. But nice thing about this parameter is that in one limit, if you specialize this parameter to 0, you recover these easy but non-local operators. On the other hand, as I send this parameter to 1, the limit is slightly singular, but we get very nice local quantities from the CFT point of view. So they are really just like zero Fourier modes of some currents of the algebra. Okay?
Sorry, is everything you're saying here, it applies just to Virasoro and
Also-
KDV as well?
Sorry?
To Virasoro and KDV and the KDV charges?
The KDV charges are this.
But what
I
is-
want to talk about. This will go to 1.
Ah, okay, because I didn't understand where the freedom is there. I thought there.
Yes, so these Q goes to 0, they are manifest in this Youngian picture. They are related to this Benjamin Ono hierarchy, which is not KDV, it's different integral hierarchy, like
Okay.
integral structure. On the other hand, this one that I kind of talk about that they are nice and so on, from the CFT point of view, they are exactly the KDV or KP charges. Okay? So what I'm trying to say on this slide is that there are different choices of things that are commuting among themselves that you might diagonalize. The ones that are easy to diagonalize, they are not so nice from the CFT point of view. Those that are nice from CFT point of view have more complicated spectrum, but they have all the nice properties in CFT. So, and they are the KP or KDV, quantum KDV or KP charges, and that's what I will talk about in the following.
Yeah, sorry, but the Benjamin Ono was this terrible structure when you have 0 times U1.
That's for n equal to 2, yes. You need the U1 for that.
You need the U1.
You need it,
And
yes.
then you have this crossover between KDV.
Exactly. So this is again one of the things that I did not go into.
Okay.
So I told you that if I add this additional commuting U1 factor, the combinatorics simplifies, but also this in these integrable structures, these two get mixed, and you cannot really decouple them, and that's what you see in this Benjamin Ono. But if you send Q to 1, then these two things do decouple. So
Okay.
at that special point, you can focus purely on Virasoro. Okay, and that's also what Alex was saying. This is this, let's say, quantum KDV. For that, you don't need this additional free boson. Okay, then you can work purely with Virasoro. Okay, and this is just a comment. This is irrelevant for the rest of the talk, but all these can be, in principle, diagonalized using. You can write Bertansatz equations for those. This is discussed, for example, in paper by Ditino. And the nice thing is that they are exactly the oldest Bertansatz equations of XXX SU2 spin chain, you know, it is known since 100 years ago, except for the fact that this interaction term between magnons is not a rational function of degree 1, which you would have in XXX spin chain, but instead it has degree 3. Okay, this is the only replacement that we have to do. Otherwise, the equations are the same. Okay, but the fact that there are these 3 factors is exactly related to the fact that here this box has like 3 directions, so that you are growing these 3-dimensional objects. Okay, that is it sounds like innocent modification, but actually it's changing everything a lot. So it's really describing field theory, and actually field theory with infinitely many currents. So a big thing. Okay. Good. Now, I don't know how much. fine, did I? Yeah, I'm quite so I have 2 slides about like how these local charges are useful and nice, but I think I can skip it. The point is that there is, if I now restrict to Virasoro, there is a classical limit of these local charges, and that limit is related to this integrable structure behind Schrödinger equation. So the space of one-dimensional Schrödinger operator is actually integrable Hamiltonian system where the time evolutions are deformations of this potential. Okay, so there are certain deformations of the potential, of the Schrödinger potential, which don't change the spectrum. The simplest one is the rigid translation of the potential, but there is also infinitely many other deformations of the potential. The most famous one is the deformation controlled by this KdV equation, which was again found 150 years ago. And this whole thing can be thought of integrable system on the space of potentials. So you can introduce Poisson bracket on the space of potentials, which is just a classical way of writing Virasoro algebra. And these deformations of the potential, which don't change spectrum, are generated by Hamiltonians, which are given by some kind of moment of the potential. So this one is generating the translation, this one is generating the KdV evolution, and so on. And they all commute, but since it's a Hamiltonian system, they are also all conserved, okay, along the flows. So yeah, and this whole thing is again one from this classical inverse scattering methods. But what I wanted to say is that there is very nice classical version of this whole thing, and the algebra itself is in some sense just quantum version of this old story. The Virasoro version goes under the name of KdV, while the W infinity version is this KP hierarchy. Okay, so that's again the difference between the two, but they fit nicely together. Now on the quantum level, these quantities that I had before, so the integrals of the powers of potential, derivatives and so on, they survive quantization. So if you now in the following few slides, I specialize to Virasoro algebras just so that the formulas are shorter. So you can write a collection of zero modes of some higher spin composite operators coming from stress energy tensor, and the claim is that for every even dimension of the local field, there is up to normalization unique choice of the Hamiltonian such that they all commute. Okay? So the commutativity with L0, the zero mode of stress energy tensor, is trivial if I restrict to zero modes, but what is non-trivial that all others commute among themselves. Okay? So this T square is basically the only object in dimension 4 that I can take up to normalization, because the other operator would be D squared T, and that one is total derivative, so it's integral, so it doesn't contribute. And starting from spin 6 and higher, there is always like unique combinations. So for example, this coefficient C minus 2 over 12 is determined in such a way that these two things commute. Okay? I have up to total derivatives, I have only these two terms, but the relative coefficient is fixed, and this happens, I guess, conjecturally, but you can check it for first 50 quantities in Mathematica, and you see that you always find unique choice that commutes with the rest. Okay? And from the Fourier mode, or from the point of view, they don't look so complicated, so you can write this one in terms of Fourier modes of stress energy tensor, and they are just some higher powers of the Virasoro generators. Okay? Yes, all these coefficients are fixed, and when you see things like 5c plus 22, they have meaning because they have to vanish in all the minimum models. So for example, these two terms are kind of fine-tuned such that they vanish in the case of Lian and so on. So these are the quantum KdV charges, and the question is...
Sure, but the last one is just a constant.
Which one? This one? Yeah, it is a constant,
So
but it's nice constant.
It's nice, yeah, but you can remove it.
You could remove it, but if you add here constant, you would be adding here something that is of lower dimension of the identity. So my claim is that if you don't do that, you include all the constants, then you get a very nice match with what I will talk about later. Okay, so it's kind of, this is like the Casimir energy, and these are kind of like higher Casimir energy of these higher spin currents, and I'm saying that they are meaningful. Okay, that's the point. So you could kind of get rid of this and also this because it's proportional to L0. So you could write just this, but it wouldn't have so nice properties. Okay, so I think it's good to do that.
But is there some, like, the way it works for the stress tensor is that we want the one-point function of the stress tensor to vanish on the plane, and then when we go to the cylinder, that explains the C over 24. Is
I
there
can
a?
try this calculation, but
There
looks
must be something
straightforward.
similar
Yeah,
that.
you could try to see if on the plane this vanishes. So every time I
I
write
mean,
these
it's better-
things, they are defined on
On the cylinder, of course, yeah.
Yeah, yeah.
I bet
I
that
think
if you
so.
do that, it works, then you get that it vanished, the
yeah,
one-point
but
function
it's
is.
calculation that one could do in like
Yeah.
15 minutes. But because you have to just transform this, and it's some quasi-primary field.
Exactly.
Yeah. Anyway, what I didn't emphasize.
Sorry,
yes.
so these are the integrals for q equal to 1, n equal to 2
Yeah,
of
but
the
okay.
equations.
Yes,
Okay.
so all that I want to talk about in the rest of the talk is always q equal to 1 for the local ones, and n equal to 2, it's just for simplicity of writing formulas. So we would be able to write this one also for W infinity. The only difference would be that you would have in between dimension 2 and dimension 4 also something on dimension 3 and so on, and here you would get contributions of these higher spin fields, but it exists and it's similarly unique. Yeah. One more thing that also Alex kind of pointed to is that I always work when I write these things on cylinder because the cylinder is the natural one from the integrability point of view where you have Hamilton and so on. Okay. Yeah, so the question is how to diagonalize these. And since L0 is part of this family and they all commute, it means that I can diagonalize it eigenspace by eigenspace of L0, so it reduces to really like finite, to diagonalization of finite matrices, you know, level by level. But the question is how to do it some kind of two orders or, you know, otherwise you can always put this thing in Mathematica and you get like a lot of numbers and you can look at their eigenvalues, but they don't seem to have any of these patterns. It's really hard to say anything. But in 90s, or maybe around early 2000s, Prochazka and Zamochikov found very nice description of spectrum of this. So they don't really kind of like completely solve it, but they have alternative description, which is convenient for many purposes. And what they did is that they map their eigenstates in the like quantum Hilbert spaces, you know, to differential operators. So the claim is that every simultaneous eigenstate of this corresponds to certain differential operator like this. So what we have for Virasoro case, we have second order differential operator, so like Schrödinger operator, in potential x to the n, where n here controls the central charge. So it's, maybe I should have called it lambda or something. Okay, but I call it n here. Then I have the energy term, which is the spectral parameter, so I have to study like one parametric family of these operators that I vary the energy. And then finally, this other term, this centrifugal force, if you want, is controlling the primary that I'm studying. So the claim is that for every, let's say, Virasoro minimum model, every primary corresponds to one of these differential operators, where the central charge enters this term here, and the conformal dimension enters this thing here. Okay?
What is Z?
That's X. That's the mistake that is propagating from my old slides. Z is X. Yes.
Okay.
Okay. You have interaction x to the n, then you have 1 over x squared interaction. Okay. So the claim of Prochazka and Zamochikov is that to every primary I can associate differential operator like this, and then this differential operator should somehow encode all this like infinite collection of eigenvalues in the way that I will discuss in the following. This is what we did with my colleague Matěj Kudra. And if you are not interested in primary but you want to understand descendants, then we have to add to this additional kind of contribution to the potential. So if you view it in the complex plane of the x parameter, we have some singularity at 0 and at infinity, which encode the central charge and the conformal dimension of the primary. And then for descendants, we just add collection of some other singular points, which have at most double pole. So far I'm not specifying what are these xj's, so I'm just allowing for some singularities at some points on the complex plane, but at most double point with this coefficient 2, plus possibly a simple pole. Okay?
But the claim is that if you look at the eigenspectrum of this operator, you will find as its eigenspectrum a relation between that and the eigenvalues of all the, because there's an infinite number of eigenvalues here. So these are
yes, but I don't, in the following I will not directly study the eigenspectrum, but I will study some kind of, again, some moments of it, some sums over all energy levels of 1 over energy to some power, something like this. But the spectrum will be encoded exactly. Just like, yeah, it's similar to what is known also in KBV, that these things can also be related to the energy spectrum. But I will not do it in this direct way, but in principle you could do that. Okay? So now I'm saying, if you want to describe other descendants, you just decorate your primary differential operator by some additional singular points with so far unspecified parameters x, j, and gamma j. So xj is really telling me where the singularity is, and gamma j in principle would be telling me is the coefficient of the simple pole. And I have roughly as many of them as is my Virasoro level. So if I'm at level 5, I allow roughly 5 singularities. There is a small redundancy about that I don't want to get into, but it's just a matter of choosing the coordinates. Okay? And now, so far I have like many parametric continuous families of differential operators, but what fixes these x's and gammas is that I impose that all these singularities are apparent. So if you locally study the Frobenius solutions around these singular points, you know that generically, if this coefficient is 2, there is resonance, so generically we will have some logarithmic terms. And because of that, for generic positions of x's, the monodromy would be non-trivial. But if I impose that my parameters gamma and x are chosen in such a way that there is no monodromy around these additional singularities, so really that these singularities are invisible from point of view of monodromy of the differential equation, then it gives me exactly 2n conditions, algebraic conditions, that look like this, which kind of quantize the positions of these singularities. And I find only finite number of solutions, and these solutions are in one-to-one correspondence to the descendants at that given level. Okay, so there is one-to-one correspondence for generic values of parameters between descendants and these rest operators, but where the singularities sit at very specific positions of the complex plane. Okay? And their positions are, I don't know if it is funny or not, but they are described by classical equilibrium positions of system of Calogero particles. So I can view this singularity as being a particle, and these particles interact among themselves with inverse square energy potential. Then they interact with some external potential, which is coming from this term, that is controlling the central charge I have. And finally, there are some particles which are kind of stuck at the origin, and those control which primary I have. Okay, so this you can view this as being like beta equations, which pick for you the correct form of this differential operator that is mapped to any Virasoro descendant that is eigenstate always infinitely many operators. Okay, so this is kind of rephrasing that Bajanov, Ukanov, and Zamochko did in this problem. Okay, so instead of describing the spectrum directly or whatever, they just said that I can map it to this system of equations and identify states with these differential operators. Okay? Yes?
This seems similar. There should be a similar story for finite dimensional quantum mutable systems.
Yeah, but
Is there some relation like
there are many systems. One similarity that this has is that if you put here first power instead of third power, then you get something like the Godin models and so on, which are more like finite dimensional integral systems and so on. But again, I feel that this third power is exactly related to this three-dimensionality of the problem. Yeah, but maybe we can talk about it later, like what integral systems we have in mind. Okay? Here, the quick connection is really to this W-algebra system, so it's just n particles. Normally, you would consider them as being on circle or on line, but here we allow them to be complex numbers. And these are like classical equilibrium positions of those particles. So now we kind of did one step, so we translated the problem of describing the eigenvectors by some collection of commuting C numbers, but I still owe you kind of answer to like how, if I solve these equations, and this is again Alex's question, how I can recover all these values. Okay, so how are these eigenvalues encoded in terms of these x's? And as far as I know, the only formula that I was able to find in the literature is the formula for the first non-trivial one, which is the I3, so the eigenvalue of p squared 0. And that's basically center of, if you ignore this factor of n plus 2, which comes from choice of coordinates, it's basically center of mass of the additional singularities. Okay? And it's true also more generally that if you go to higher ones, you get some higher, expectation value of square, of x's, cubes, and so on. So it's always some symmetric polynomial of these x's. But as far as I know, no one really wrote kind of explicit formula for those or found some kind of explicit algorithm which allows you to produce formulas like this and really get the numbers. So this is what we did with Matěj using this WKB approximation, and it was finally out last year. And yeah, we worked for more general rank of the algebra, so not just for Virasoro, but for this WN algebra. Okay? So in that case, the Schrödinger operator, the simple form is just replaced by the nth of the differential operator. Okay, but again, a lot of calculations are similar. Yes. So now, in the following, I will focus exactly to this family of non-unitary minimum models, which have a property that they are simultaneously minimum models of Wn algebra and also Wk algebra, where n and k are two coprime integers. And it's some subclass of non-unitary minimum models, which, for example, are relevant because they are the VOAs that are associated to this Argyres-Douglas superconformal theories in 4 dimensions. But they have many other nice properties. And on the level of box counting, what is nice about this is that they look like here on the left-hand side, that there is no, it's missing this offset away from the wall. So they are, the primaries are labeled by just kind of this staircase pattern. So they have only one allowed asymptotics and many things like simplify. But the analysis is, I believe that the analysis will work in general. Okay? But one thing that I should say, if you look here, is that everything that is here is anyway some rational function of n and of k. So if you derive formulas like this for any n and k integers, then you know this formula even for non-integer values of n. So specializing to this is like no loss of generality when if you care only about finding formulas like this. Okay, but the geometry of these algebras or these minimum models is slightly simpler. So the calculation that we did is following kind of suggestion that was mentioned in this lecture notes by Dory, Negro, and Tatel, where they basically say that one should apply the form of WKB expansion to these differential operators. Okay, so you have differential operator and you kind of try to solve it using WKB. So here I wrote the nth order differential operator, okay, but you can just replace this by that Schrödinger operator that I had two slides before. So the way you do is that you start with this differential operator and you write formal ansatz for eigenfunction, something that is annihilated by this operator, of the form exponential of integral of something, and this something is formal power series in h bar times 1 over h bar. So this is the standard WKB ansatz. By the way, I did one more thing that I didn't mention. So by rescaling the coordinates, I traded this energy term for the Planck constant, but you know, you can trade one for the other. So it's convenient to have the Planck constant there. So the WKB expansion in this case is also like large energy expansion. So we use a link to infinity, if I remember correctly. So if you plug this ansatz here, and you require order by order for this to annihilate this, then you find at leading order, so this is the classical limit, the genus 0 limit, if you want, you find a WKB curve, which is some plane algebraic curve sitting inside of C2, which is given by this equation y to n plus x to k is equal to 1. Okay? And this is the geometry that controls the whole WKB expansion. Okay? Some people call it Catalan curve when n is equal to k, people call it Fermat curve, but we care about, for simplicity, for greatest common divisor of k and n to be 1, so in that case it has genus k minus 1 times n minus 1 over 2. Okay? So this is the zeroth order kind of thing that we get from this WKB expansion, and then this is how it looks like if you project to three-dimensional space in the case of, let's say, W3, W4 minimum model. So that's certain minimum model of central charge minus 114 over 7, and you see that it kind of has genus 3 if you trust this picture, but actually it really has genus 3 as you can count with everyone with its formula. If you want, you can represent this curve faithfully using certain, you can using certain tiling of the hyperbolic disk. So if you cut out this inner polygon and glue it in certain way along the sides, you exactly get that.
Sorry, what is the surprise about the genus? That Newton polygon is just a triangle, as I understand, yeah? And for co-prime n and k, you just count the points inside and get what you want.
So that's how I would calculate the genus. Honestly, here, I have better picture for this. Yeah, this picture. So this is like your higher genus, whatever thing, and you can project it to x coordinate or y coordinate, and you can count how many pre-images there are. So generically, if these two things don't cancel, then there are n choices of y. If you know the x coordinate, the other way around, and this way, you can count. Away from the branch points, it's very easy to count how many points there are on this curve, and then on the branch points you have to look how it's branching, and from that you can calculate the genus. Okay, so it's quite straightforward.
You can do a tropical count, which I think you mean.
Well, I mean, just this plane curve with Newton polygon is much simpler, much simpler.
Yeah, if you know stuff, if you know the Newton polygon, how to use it, then it's yeah.
Okay, you wrote that I just asked. Is it just this triangle? Yeah, and so which gives you this.
So the triangle that means is really the Newton polygon. Yeah, you can count it in that way.
But there is no surprise that it's smooth curve, right?
Yeah, but for this, if this is 0, then it is rational at singular, and for any non-zero value of this energy, it is smooth. Yeah. So I consider this smooth case. So, but you can really study it in detail, and this is what we did with Matej, and we spent a lot of time on it, but it wasn't so important. You can really put explicit, like let's say hyperbolic metric on it, and study the geodesics and so on. And it's one of the examples of geometry that you can really like uniformize explicitly using 19th century thing like hypergeometric function and so on. The reason for it being the fact that if you project it not to x plane or y plane, but all the way to this t plane, which I didn't introduce, but basically I define new coordinate t equal to x to k. Okay? If I project it all the way down, then I end up with three-punctured sphere. Okay? And this three-punctured sphere is exactly what is kind of controlling all the calculations that we are able to do. By the way, there is one thing that I was confused about, but this resolves the thing, which is that from this formula, you expect the eigenvalues to be just some polynomial functions or rational functions of the parameters, but from this WKB curve, it's higher genus, so you would expect some transcendental functions in principle if you calculate the periods and so on. Okay? But you know that the answer has to be rational or rational functions. And the reason behind it is exactly that the curve has a lot of automorphisms, like a big symmetry group, and if you quotient out by those symmetries, you end up with this three-puncture sphere, and all the calculations are effectively taking place there. By the way, I strongly believe that this three-punctured sphere is exactly what one sees in this again, topological string calculation. So what we are doing is some kind of, in some sense, studying this box counting problem in the limit where there is like large number of boxes, and then it's known in math that this is captured by this limit shape, which is again kind of encoded in this three-punctured sphere. So if you are familiar with topological strings, which I'm not that much, but there is like this A model, topological A model with C3 target, where the description of partition function is in terms of this box counting problem. On the other hand, if you calculate the same partition function but using mirror symmetry, using the mirror curve and B model, you are exactly evaluating some periods on this three-punctured sphere, and you get the same answer. So this is kind of what is happening here. Yes.
So, I mean, yeah, can you go back to this statement argument? So, I mean, besides topological considerations, can you map them as Lagrangians in some syntactic?
What would be the Lagrangians?
I mean, for example, the curve that you gave for the Argyris diagonal theory
This one?
is a Lagrangian in C2, right?
Oh, I guess maybe for some
Yeah, there is a syntactic
reasons.
structure that plays a role in all these WPDs there. And likewise, the mirror curve of C3 is a homomorphic Lagrangian to start with the star.
Yes, so if you write the mirror curve in the usual way, like e2y plus e2x is equal to 1, then in certain well-defined sense, this is just like large n and k limit of that, and that you see also on this combinatorial picture, because n and k controls these things, and as you send them to infinity, then you are again recovering this counting that was, I don't know where it was here. Okay, so they are somehow like finite calculations of this mirror curve there. And you see the level of the periods, as I mentioned at some point. Okay, but it's not just that I see three-puncture spheres and I said that it's the same thing. You can also study. Yes, also I forgot to say one important thing in this first line. So the leading order WKB expansion gives me the curve itself, while all the subleading, like H-bar corrections, give me infinite collections of meromorphic differentials that live on this curve. And then the spectrum, that's the claim, is obtained by just calculating period integrals of all these things. Okay, and that's what we did explicitly. You can do the calculation. Doing the calculation here would be complicated, but you can kind of push the one forms to this this is what I call mirror curve. But there they are no longer meromorphic differentials because they have some kind of branch singularities around those three singular points. But the monodromy of those is captured by exactly these lambda parameters of the algebra. So for example, what I had before, this Calabi-Yau three condition or whatever, is exactly telling me that although these differential one forms are not single variant as I go around these singular points, the phase that they pick is exactly including the parameters of the algebra. And furthermore, if I make loop around nothing and kind of pull it over to have loop around all three of them, then I get well-defined answer exactly because of this condition. So you can really associate the parameters of the algebra with the three individual punctures. Then I still didn't tell you how to integrate it in sense like what contour to choose, which cycle. And in principle you can imagine many, like n-1 times k-1 cycles here. But fortunately, they all come from lifting a single simple cycle that you can draw on this three-puncture sphere, which is just this Pohammer contour. So the property of the Pohammer contour is exactly the fact that it goes once in positive and once in negative direction around each of the singularities, so that this multi-valuedness of the one forms that we are integrating doesn't play any role. So the phases kind of cancel and the contour really cancels. And if you look how these contours look like on the WKB curve itself. In the x and y plane, they are just this type of figure 8 contours around the branch points. Okay? There are other things, but I guess I'm slowly running out of time. Yes. So, yes. So it's the geometry that is here is really very nice. So basically, all the whole homology of the WKB curve comes from just lifting this Pohammer contour. So it gives some nice over-complete basis over integers of this first homology group. It's not a symplectic basis, but it's a basis which respects the symmetries of the curve that it has. And if you study intersection pairing of these cycles, you recover other aspects of the algebra, so you can really see there this fundamental cube and so on. So every cycle intersects with 6 other neighboring cycles, which exactly correspond to these 6 other dots, or to these 6 factors here, and so on. So there is a lot of algebraic structure that is kind of recovered by just looking at the geometric properties of the thing that is here. And finally, as I kind of promised you before, we were able to identify the eigenvalues of these integrals of motion exactly with these periods up to normalization, which was never really fixed at any point. Okay, and this formula doesn't apply only to the highest weight state, which I showed at some point, but it really includes all the descendants. So all the information about descendants is just contained in these periods. And furthermore, all these integrals can be really explicitly evaluated because they basically reduce to some beta function integrals that are here. Okay? So we can produce algorithmically many formulas like that. So yeah, we checked. It's like I cannot write you the formulas because they are quite ugly, but we explicitly checked many terms, and they respect the symmetries, and they agree with like numerical evaluation of these eigenvalues of the matrices. And then there is this comment on the large n and k limit. So for some reason, which I'm still a little bit confused about, if you calculate this ground state spectrum, so these Casimir energies, and take the limit of large n and k, you recover kind of the keep going to 1 expansion of the McMahon function, which is kind of what you would expect from the B model calculation. But it's a little bit confusing because this McMahon function, the way I understand it, is like counting states from the A model point of view. But here we are not counting states, but we are really looking at eigenvalues of Hamiltonians in single state. Okay, so this is a little bit. It feels a little bit like some integrability trick where the eigenvalues are given as traces over auxiliary space. So there's this kind of integrability, like general integrability property that the integral models have, that they represent the spectrum as traces over some auxiliary space. Okay, but I'm not sure like if this is really the reason. Okay, yeah, fine. And then finally, and this was just like kind of advertisement for maybe next time we are here, that we are currently studying what happens if you study these ij's not as individual numbers, but if you study the whole generating series of them. So you know, this power series is like formal power series, and it's not convergent, so you can try to sum it using Borel summation. But in the Borel plane, there is really interesting pattern of discontinuities and singularities, which are somehow capturing the 4 BBPS states of this Argyres-Douglas theories. So there is very nice kind of like resurgent structure of this like quantum mechanical problem. So these quantum periods have very rich analytic structure. There is, for example, this BDP formula, which tells me how these Borel sums jump as I move along with the phase of the Planck constant, and basically everything should be encoded somehow by the intersection matrix of the cycles. So I'm hoping that if I understand better the geometry of these cycles, I will be able to understand better this analytic structure. Okay, so that's the goal that we have in Matic. And maybe one, this is the final slide, I guess. So one nice thing that you learn from this kind of exact WAB calculations is that there is very well defined and nice kind of algorithm or procedure which allows you to study spectrum of Schrödinger equation, let's say in polynomial potential, from just two pieces of data from classical periods and from just one number, one classical period for every cycle, and then some global topological data like which period this interacts with each other. Okay, and once you fix this data, which is really quite few data, it's just a few numbers and some intersection matrices, then there is very smart algorithm or formula, which is this TBA equation, which automatically spits out all H-bar corrections, not only all like power series corrections in H-bar, but also all the non-perturbative corrections, so like kind of this instantaneous effects, completely using just this very simple data. So this is something nice that I think people should know more. And it's not really too difficult. It all comes from this discontinuity formula. Okay? So this is where we are now. So hopefully in a year or two you will understand everything completely. So thanks. This is maybe for Julia and Alessandro. This is the first picture that I took 19 years ago when I went to CISA as first year student, you know, at Sarakus. Yes. So it's still the same, no?
Are there more questions or comments? Pasha, please.
I want to ask about special values of central charges for this W-algebra. So there are examples, for example, Wn plus Heisenberg with central charge n, and I think, so is it true that in these examples these beta equations trivialize? And another case for this quantum KdV, I know that there is C equals minus 2 symplectic fermions, which is also exactly solvable. So is it the same type of example, or do you have several different cases when this equation is simplified?
So C equal to minus 2, I think that's kind of the easy point. I mean, there are like 2 points roughly where the algebra becomes linear and things simplify a lot, and one of them is this C equal to minus 2. But I think Bažanov and Zamolčíkov gave the formula for this, for example, i's in the C equal to minus 2 case. You see that also, here you don't see it, it's minus 3, but there the spectrum is known. For the other case, where you have central charge n, there I don't know how it would simplify. One thing is that these equations are non-trivial even for n equal to 1, which is just a free boson. So there is a very rich structure of, even for free boson, these are complicated. This is what I talked about a little bit like 3 years ago, but we never finished the paper because I was too lazy to finish it. But even for C equal to 1, C equal to 1 and n equal to 1, these equations are kind of complicated. So the advantage of these equations is that they are as complicated in the general case as they are already for the free boson in some sense.
Okay. And what technically happens when C equals minus 2? Do this interaction terms cancel or not?
I think what happens for C equal to minus 2 is you can just represent the Virasoro in terms of, I think, fermion, and then they become bilinear, something like that.
No, I understand this, but is it visible at the level of beta ansatz? Like, does it trivialize or?
At level of this one, I would not expect it because this one describes the whole W infinity and the specializations show up in complicated way as some kind of null states. So this one does not really work well with that. The other beta ansatz, which is this, here maybe you could expect some simplification because this one is kind of tailored to Virasoro algebra. This is, I didn't talk about this today, but you know, this one has much better chance of simplifying for Virasoro C equal to minus 2 or something. But I didn't look at this, so I don't know. But since you know all these, all these, maybe that would mean that you could write the better roots in simple way. Yeah.
Sorry, but if you have a free boson, can you fermionize it also? And but in this case, don't you get anything like bilinear generators?
So if
For
you
free
are
version.
at the general, if you have with general parameters, then you do something like fake-in, Fuchs kind of representation.
No, it's for general parameters, but
For general-
for C equal
For
1.
special, yes. For single one, I don't remember, but I don't think.
It doesn't look so, yeah, but...
Yeah, I think the point that there are these two simple points, which is free boson and free fermion, and I think for free fermion it works that they become bilinear. For free boson, I don't think so.
By free fermion, you mean C minus 2.
Psi bar psi, yeah, I think it's C minus 2 and psi bar psi. That everything becomes just derivative of psi bar times derivative of psi bar, something like this. So I think this point is simple, and the other one, the free point, where you would just write P as Sugawara d phi square, I think that one does not simplify and it's still nonlinear and so on. But you know, it's been many years that I looked at this specific point.
Sorry, I have a basic question. You have two types of beta equations. So you have multiplicative kind of beta equations with U's, and you have the additive equations like then
Yes.
whatever with X. So and you propose the formula to get the I1, I3, I5 eigenvalues from X, like in terms of the rules, beta rules from the second
For
equation.
the additive ones.
Yes. Is there a formula from the multiplicative ones?
There is formula that looks kind of like this, but it's like brute force calculation, more or less like fitting data. No, there is like a closed form formula for these ones in that case, but it is in the context of this ILW for any Q, and then to extract these local ones, that I don't know how to do.
So
That's very complicated.
that's the slightly singular, the limit. which
Yeah,
is
I call it slightly
singular.
singular there, but actually if you try to take this limit on this level, I think it's very singular because I don't know what is happening. Because you have to sum over all partitions, like usual partitions of free boson, and then the poles, there are like one quadrant of plane where there are poles. It's a little bit like this Nekrasov's Q2 characters or something, that there is more and more poles everywhere in that quadrant, and somehow if you take the order of limits in opposite way, you can extract out of these smooth things like this, but I don't know how to do it. I would really like to be able to write that, but it looks really complicated. Like if you understand the Q2 characters and similar things, maybe you would see how to do it. But basically it involves this sum over all Young diagrams with singularities having at all the boxes of the Young diagram, and you have to extract out of it something smooth, so there has to be some very non-trivial cancellations there. So I wish I knew how to do it, so we did it like 3 years ago by just brute force calculating first 3 or 4, just to see. And the result, that's the surprising thing, the result looks kind of like this. So again, you get equations that are polynomial in those methods. But as you said, one system is additive, one is multiplicative, there is no
So
obvious
is
method.
it kind of a GLM duality, like
It
spectral
feels
duality?
like something like that, but I
And
can't remember.
the number of beta roots on both sides, how are
That
they
agrees.
related?
The number of beta roots is always the level of the Virasoro. But one thing is that, that's what I didn't talk about, there are like 2 spaces. If you write, yeah, I didn't write the formulas. These beta equations, these x's seem to live more like in the worksheet, in like CFT space, while the other one, the multiplicative ones, seem to live in the spectral parameter space. So I think they live in different space also.
Do you
Generally
have
do.
an R matrix formalism for the second type of beta equation?
For the local ones or for the?
Because for multiplicative, I understand.
Yeah, for that I know, for this
that
one I
type
don't
is
know.
one.
I don't
For
know.
this you don't know.
I don't know. I also don't know, by the way, I also don't know how to do the Q deformation.
Yeah, that's
So
what
this one
mine
also
was,
works only for
but
Q to the
mine-
1. I don't know what happens as Q is not 1. That would be also very nice, but I'm not even sure if it is possible, like, because this one you don't need to calculate this auxiliary free boson, in the other one you need to, and so on. So it seems, if I was just repeating what the literature says, then, well, I'm not sure if I completely agree with it. This one is more the integrable structure associated to this UQ SL2 hat, that people study. So this like, the BLZ quantum group. While the previous one, it's not quantum group, but it's like Youngian free boson. So even the symmetry algebra seems to be different. If you kind of just repeat what the literature says. But I'm not sure. You know, definitely there must be a map because you are still diagonalizing the same
So the
Hamiltonians.
multiplicative side is okay. There is a Q deformation there, as we know, like this quantum toroid or whatever. So it's okay. But the additive ones you say is not okay.
Yeah, and also this one is much more sensitive on the rank, while the Yangian one, the multiplicative one, is completely blind to the rank of your algebra. It works, like I said, as well for free boson as it works for W25. The only thing is that changes when you change the rank of W-algebra is the number of terms that you have in this external field. So the length of the spin chain, that's the only thing that changes, but not the underlying kind of integrable structure. While for the quantum KDV and so on, it really seems that you have different quantum group for every rank and so on. I don't know how to do those things uniformly. Yeah, sorry.
Yes, maybe we can postpone the discussion to private level. Okay, we thank.
Thank you.